Hello, I am Petros Anastasiadis from the National Technical University of Athens, Greece, and today I'm going to present you my work for the PhD forum of IC High Performance towards a heterogeneous data-centric framework for efficient linear algebra. So, BLAS is extensively used in scientific code. For this reason, all vendors provide optimized libraries for performance on their own architecture. In the case of heterogeneous architectures, though, these libraries are still unable to harness the full performance available. The previous approaches for hybrid BLAS routines for heterogeneous environments were either system, architecture, or software dependent, or focused on optimizing some aspect of the problem for some common execution scenarios. Our proposed approach is a portable, high-level framework which will offer hybrid BLAS routines with unmodified BLAS API for backwards compatibility, will utilize existing optimized BLAS libraries from vendors for computation, will implement automatic data distribution for the heterogeneous component, and will include a lightweight prediction model, which will ensure optimal hybrid performance. All this in a high-level structure, which will allow contributing to this framework to be easier. The model proposed for this framework is the following. We split the data on worksets, and for each workset we assign on a heterogeneous execution unit, which can execute the data part available in parallel with other execution units. The total time for this scenario can be seen in equation 1. Then we model data movement between different units through data links, for which we calculate their bandwidth and latency seen in equation 2. Finally, to allow unit-wise communication and computation overlap for further performance improvement, we split the worksets on smaller subsets called subkernels, if needed, of course, and the total time for each unit can then calculated by equation 3. We evaluated this model on a dense matrix multiplication on 2 different systems. For the model, we used the semi-empirical approach. We calculated the latency and bandwidth with 2-value sampling, and the subkernel GPU and CPU execution times with least squares linear regression on a train set on 1000 samples of sizes between 1000 and 6000 for M, N, and K. Then we validated all this model for 4 different classes of M, N, and K with varying workset sizes and subkernel sizes. The results can be seen here, where we compare the predicted with the observed values. As we see for both systems, we have a really low mean percentile error, which is good, and the mean and the max errors appear in the lower bottom low performance areas, which are less interesting for optimization anyway. Then we can also notice that in the case of system 2, the data is scattered through the plot, which is because performance is greatly impacted by the low bandwidth and the subkernels. Then we implement the whole proposed pipeline for 2 scenarios, an SPM-VCSR execution on the first system and a dense matrix multiplication on the second system, and compare them with optimized vendor libraries which were available for these cases. For our implementation, we used curve fitting on equation 1 to get the optimal CPU and GPU ratios as different units for the CPU and GPU. And in the case of the red proposed bar, also to find the subkernels for the optimal communication and computation overlap. We also use the same values for cuBLAS-XT, which is already hybrid library given by Nvidia for its cards, and we compared all this. As you can see, our implementations are very good, not only for hybrid-wise, for CPU, GPU parallel execution, but the subkernels also further improve performance a lot by communication and computation overlap. This was my presentation. Thank you all for your time, and I wish you to stay healthy. Bye.